Hello everyone and welcome to our video presentation about the NumPy project. We are Robert Koning, Proveer Mulchand, Jim Verheijden and Erwin van Tiel, and in this video we're going to tell you something about the architecture behind this amazing open source project. So, what will we talk about in this video? Well, we'll first give you a short introduction to NumPy and its functionality. Then, we will dive deeper into the architecture behind NumPy, and after that we'll discuss how contributing to NumPy works. Finally, we'll tell you something about the projects that make use of NumPy. Let's start with NumPy arrays and why they are cool. So, NumPy characterizes itself as the fundamental package for scientific computing with Python. It contains arrays as data types, but also has functionalities for linear algebra, Fourier transforms, and random number capabilities. NumPy is written in Python, which is a beginner-friendly programming language, and therefore the library itself should also be easy to use and understand. So let's have a look at some code. Let's start by importing NumPy as NP. Then we create a 3x5 array with 15 elements and print it. We can now check the shape, dimension and size of the array. With NumPy we can also easily retrieve the first row or first column of this array, as you can see below. Transposing an array is also very easy with NumPy. You just have to type np.transpose and NumPy does all the work for you. We can also use the linear algebra functionality of NumPy to compute eigenvalues and eigenvectors. Finally, we can even use the random number capabilities to generate arrays full with random data. We have now seen quite some Python code, and as you have seen, this code is fairly easy to use and understand. But NumPy is actually not completely built with Python. There's actually a fair amount of C code doing the hard work under the hood. We'll tell you more about that in the next part about the architectural style.
The NumPy library uses a component-based architecture, meaning that the different functionalities of NumPy have been separated into different components. The inner components have been written in C for speed and contain Python wrappers to make them available in Python. We will now elaborate on the 6 most relevant components. The core component contains the implementation of NumPy arrays written in C. This implementation deals with low-level problems such as memory management and indexing. The linal component contains functions for linear algebra, the random component contains random number generators, and the FFT component contains functions for fast Fourier transformations. The core, linal, random and FFT components have all been written mostly in C. The f2py component is an interface to use NumPy with Fortran. Fortran is an older programming language for scientific computing that is still in use today. The lib component contains library functions in Python that interact with NumPy arrays. Most NumPy users will interact with the lib component.
We will now briefly view NumPy from a runtime perspective. When doing so, we can see that it depends on several runtime libraries. These are BLAS and LAPACK. BLAS, which stands for Basic Linear Algebra Subprograms, is a specification for vector and matrix operations, such as multiplications and dot products. LAPACK, which stands for Linear Algebra Package, is also a specification which defines linear algebra operations for matrices. Examples of these are least squares, eigenvalue problems, etc. LAPACK uses BLAS under the hood to leverage the speed bonus of fast BLAS implementations. Both BLAS and LAPACK have different implementations as they are an interface specification, but they also have a default reference implementation. Other implementations are aimed at compatibility with more platforms, such as Atlas and OpenBLAS, while others focus on the highest performance by focusing on a single platform. Take for example Intel MKL, which as you might have guessed focuses on getting the best performance with Intel CPUs. To show the difference in performance between these implementations, a benchmark was run on different tasks, namely taking the dot product of 2 vectors and performing an eigendecomposition on a matrix. This logarithmic scale chart shows that different BLAS LAPACK backends can have a significant impact. When comparing the Intel MKL version to the default reference implementation, this results in a runtime increase from only 3 seconds to 50 seconds, which is an 18 times increase. This shows that it is important to look at the architecture from multiple architectural perspectives, as it can give new insights that would not have been obtained otherwise by only doing componentization, for example.
An important aspect of an open source system is of course contributing.
When a programmer wants to contribute to NumPy, there are several different possible activities to take part in, and it's not only about code. Examples of other activities could be website development, translating content, fundraising, or writing technical documentation. The most important activity, however, is writing code. So let's take a look at the workflow of code development in a little more depth. When contributing by means of writing source code, NumPy specifies a set of guidelines in order to keep the code base and version control organized. To guarantee working code, test code has to be provided with every code edition. NumPy asks its contributors to program in a test-driven development fashion, and contributors are requested to first write the failing tests and after that write the functionality to make the tests pass. Besides guidelines about testing, NumPy also specifies guidelines on how to format commit messages. Every commit message should be formatted in such a way that the nature of the addition becomes clear from the message. Examples of types of commits are bug fixes, deprecations, maintenance, enhancements, and documentation. Finally, a release note must be written that specifies the changed or added functionality before your pull request gets merged. We know from our own experience what it's like to contribute to NumPy. We are currently working on a contribution that we aim to present as an enhancement. It concerns a modification of a function that splits an array into subarrays. Currently, NumPy's split function only deals with one-dimensional arrays, but we have generalized it to handle n-dimensional arrays. During multiple review iterations on our pull requests, we noticed that NumPy's developers respond quickly and come up with clever solutions to problems you run into. This is also the case for documentation contributions that we made. Basically, there's a lot of communication going on, even for small additions, and this shows the thorough methods of the NumPy developers.
Considering NumPy as a library, it is most useful as a part of other projects. These projects then don't have to focus on the implementation of fast arrays, but can focus on their own functionality. An example of a prominent project using NumPy is SciPy. SciPy, short for Scientific Python, is a set of open source software for scientific computing using Python. NumPy is a core package of SciPy, and some of SciPy's other core packages are built upon NumPy. The SciPy library is part of the SciPy ecosystem and is built upon NumPy as well. It is used for more complex mathematical operations on arrays. Matplotlib is a plotting library for Python and is also one of SciPy's core packages. Apart from SciPy's core packages, some other well-known projects that our peer groups have studied also use NumPy. For example, scikit-learn, which is a machine learning library for Python and an extension of SciPy that uses NumPy and Matplotlib. TensorFlow, which is used for machine learning and big data processing. SpaCy, which is used for natural language processing. And Ludwig, which is used for machine learning. There are many more projects that use NumPy, ranging from small hobby projects to professional solutions. According to NumPy's GitHub page, it is used by 341,000 other projects hosted on GitHub. In this video, we have shown how the architecture behind NumPy provides a foundation for a fast and easy to use library. Therefore, it is no surprise that it is the basis for many data processing libraries that are used today. For more information, please see our blog posts on the course website. Thank you all for watching.